Alright, now we're going to turn to regression. Regression is, it's kind of like what we've been doing, except we're going to use the linear property, the linear relationship we see to actually come up with a line that describes the data. So what we call the regression equation, or we call sometimes the line of best fit, is an actual line, that an algebraic line, like mx plus b. Instead of using m, we're using this b1, mx plus b, and then this b naught represents the like the y-intercept. But this is going to describe an equation that's going to describe the relationship between that x and y variable. Alright, you'll hear me refer to it as the regression line mostly, but sometimes I'll call it line of best fit or the least squares line, which we'll get into later. Alright, notation stuff. If you're doing stuff for a population, you use the capital or the Greek letters, beta sub 0 plus beta 1, but normally you're doing it on samples, so you use the lowercase b's there. Requirements, just like before, you got to take a simple random sample of some type of numeric data, quantitative data. You look at a scatter plot and you see that straight line pattern like we talked about. And then if you have outliers, remember to remove those outliers because they can really throw things off. Alright, these are formulas to determine the slope and the y-intercept. There's the actual r value that we just talked about. This is standard deviations of the y values, standard deviation of the x, but we're not going to compute these by hand. Your calculator is going to compute these values for you, so that's where we're going to get those from. We're just going to need to be able to use it. Alright, the regression line is always the one that fits your points the best. So here is a sample of data. Alright, so 15.35, this is the cost of pizza over years, and this is the cost of subway fare over certain years. Alright, if we ran linear regression on these, which we'll do on our calculator in a bit, we come up with these equations, right? Which is the same. This is just in different forms. Mini tab, stat disk, Excel, TI-8384. This is mainly where we're going to get ours from. But just notice that they all give the same thing. The y-intercept is 0.0345, 0.0345, 0.034, well 6, rounding it to 4 places. Right, 0.034. So all of them have that same y-intercept, and then the slope 0.945, 0.945, 0.945, 0.945. Alright, so what we come up with in all cases is this equation. Alright, no matter which technology we used. And this is what we're talking about. This describes the relationship between the x value, the cost of a slice of pizza, and the interpreted y value, or the predicted y value, the cost of subway fare. So you tell me what a slice of pizza cost, and I'll tell you an approximation for what the subway fare is by taking that cost of the pizza, multiplying it by 0.945, and adding this 0.0346. Alright, so that's what this is doing here. Alright, so we're going to graph this equation just so you can kind of see what's going on here. So this is that line. The red line is this line, y equals 0.0346 plus 0.945x. Alright, graphed in an xy plane. So we saw this scatter plot earlier, and this is the same exact scatter plot with now this line going through it. Alright, so these green dots were our data. These are the actual data. Alright, and we use the red line to represent what basically we would expect the prices to be. So let's say that I'm in a town, or in this particular town, and the price is of a slice of pizza is $1.50. Alright, we put $1.50 into that equation, we get this out, which is pretty close to $1.50. Alright, so that means it would predict the Subway fare would be around $1.50 when the pizza slice costs $1.50. Okay, so that's what that line is for. It just gives us a way to predict unknown values. And literally what we're doing is we're just taking a pizza price, plugging it in here where the pizza is, multiplying it by this, adding this, and that gives us our Subway fare. Alright, now, do we always plug it into that line? No, not always. Okay, that's what this little flow chart's telling you here. Is the regression equation a good model? Alright, if it is, meaning that the line graphed and scatter plot shows the line fits the points well, like this one fits them very well. They're all kind of tight around that line. I don't have any points way down here or way up here. So it fits the points well. R indicates there's a strong linear correlation, and the prediction is not much beyond the scope of the available sample data, meaning that we don't have pizza slices that are like, you know, $7 or something that are way up here. Right? We don't have Subway fare that's, you know, $4 and $5. It's way up here off the chart. That's what that last thing is saying, beyond the scope of the available data. Right? If all those things happen, then it is a good model. You just substitute the value of X in, like we've been talking about. Plug it in there and see what the Y value comes out to be. Alright, if it's not, well, then we're just going to take the average of the Y values. Remember, X with the bar over it meant the average of the X values. Well, Y with the bar over it means the average of the Y values. So, if there doesn't appear to be a strong linear correlation here, meaning the R values, you know, small, 2, 0.2, 0.1, something like that, close to 0, then I'm just going to take the average of the Y coordinates, all these points. Remember, every point has an X and a Y coordinate, and I'll just take the average of all those Y coordinates and let that be my prediction. Alright, so that's basically what this is saying. Use the predicted value if it is a good model. Use the equation. If not, use the mean of the Y values. Alright, this applies to linear patterns in your scatter plot. Alright, this last little idea, this is called a residual. The residual is the Y that we observe, the actual Y value from the data set, minus what the linear equation would predict it to be. Right, and this is for specifically the points that are on the data set, on the actual green points. You can't produce a residual if it's not already from the data set, meaning that there's nothing here above it, so I can't produce a residual for 75-cent slice of pizza that costs 75 cents. It can only be one of these actual dots that are on the graph. Alright, and that's what these residuals are. So this dot missed the line by 11 values. This is the actual. This is where it was predicted to be on the line. So it missed by 11. Alright, this residual is below the line and it missed by 5. So it's 5, but because it's below, it's a negative number. Okay, same with this one. This dot is the actual value from the data set. It missed the line below it, and it's below it by 13 points. So it's a negative residual. Right? This is a positive residual. Right, plug it in, and the actual point was 7 higher than what the line predicted it to be. Now notice when you add these together, 7 and 11 adds to 18. 13 and negative 5 add to negative 18. And positive 18 and negative 18 add to 0. Right? So these residuals should always cancel each other out if you add them all together. Alright? That'll always happen if you have the least squares line. Now, we could put a million bajillion lines in here. Alright, we could put a line that goes through like this, a line that goes through like that, a line that touches this one and touches this one, so it just goes through like that. Right? There's all these lines that we could put through here. There's an infinite number of lines that we could put through the data. But what we call the least squares regression line, if we take these residuals, this distance here, this distance here, this distance here, this distance here, and we square them, literally making a square out of these things. That's why these things have these squares drawn around them. And then we add up all the areas of these squares. This plus this plus this plus this. The line that causes the area of these squares to have the smallest sum is what we call the least squares regression line. Right? And that's, again, what we were saying earlier, is another name for this line. Alright, the least squares line. Alright, that's where it comes from. Taking all those residuals and squaring them, the line that makes all these squares have the smallest sum, the area is the smallest, is the least squares regression line. Alright, and that's our line of best fit that we use.